Hello guys, this is Ashutosh, your host, and I welcome you all in this new video tutorial lecture of power electronics where I have presented, you can see over here, today our topic is 3-phase half-wave controlled rectifier. As you can see in the diagram, these are the waveforms at the right side. And with resistive load, I have connected resistive load, which is purely resistive load. Then I have taken 3-phase supply source and 3 thyristors T1, T2, T3 are connected in each leg of each phase. So guys, what happens? This is called 3-phase half-wave converter, which combines 3 single-phase half-wave controlled rectifiers in one single circuit, okay, and feeding a common load, which is in our case purely resistive load is there. This is purely resistive load, okay, and these are connected. This you can call this single phase rectifier. This is also single phase rectifier, and this is also single phase rectifier. So all the 3 single phase rectifiers combines, and it constitute 3 single phase half wave controlled rectifiers in one single circuit, feeding a common load of purely resistive load. So thyristor T1, as you can see here, this is T1. Okay, this is T1, thyristor T1, and you can see in the PowerPoint presentation here, you can see this is okay 3-phase half-wave thyristor converter with resistive load. So this is our first leg of first phase. This is the phase of A phase, this is B phase, and this is C phase, and basically it is star connected. Okay, this is star connected and neutral. So one point is connected to resistive load, positive terminal of resistive load, and other point or neutral is connected from negative terminal of resistive load. So this constitutes of this 3-phase half-wave thyristor converter. Okay, now see what happens. See, 3-phase half-wave controlled rectifier with resistive load. So this is basically 3-phase waveforms. And what happens here, guys? This is X point, this is Y point. When both are interconnects, 2 phases are interconnecting here, intersecting here. So this is the start point. So here alpha is 0, means firing angle for thyristor 1 is 0 degree. Triggering angle alpha 0, alpha is equal to 0, and the thyristor T1 conducts from 30 degree, omega t 30 degree up to 150 degree. So this is the conduction angle of T1. As you can see here, you can see omega t equal to 30 degree to 150 degree for T1. T1 conducts, it is triggered at omega t equal to 30. And alpha is equal to triggering angle alpha equal to 0 degree. Okay, then it will conduct up to 30 degree up to 150. Then it is turned off. Okay, and then T2 conducts. T2 is triggered. As you can see here, Y is the point where T1 turns off and T2 starts conducting. This is T2, thyristor T2 of second phase. So the conduction angle of T2 is from omega t equal to 150 to 270 degree, and T2 conducts up to 270 degree. Then it will be turned off at point Z, and thyristor T3 starts conducting from 270 degree, and it will conduct up to 390 degree, guys. So it becomes 3-phase half-wave controlled rectifier, and you can see output voltage is like this in purely resistive load, and output current is the same. Okay, so now you can see in the simulation the waveforms are similar. You can see here, this is sine wave. Okay, you can go to simulation, run simulation, then select these sine wave, all the three sine wave, add these sine wave, then there will be polyphase, three-phase supply like this. Then you choose output voltage V load. So this is the waveform of output voltage, you can see. Then output current is selected, and this is the output current. So our PPT, what is in our PPT is the same waveforms as you can see here in the simulation diagram. So these are the same waveforms when resistive loads are connected across this. And the firing angle is alpha is equal to kept 0 degree. Okay, then you can see the next diagram where alpha is kept 30 degree. From this diagram you can see three thyristors are same, but now polyphase supply is same, but now the triggering angle is changed. Now alpha is 30 degree. So conduction angle of T1 becomes after difference of 30 degree. Guys, you can see here. Okay, when alpha is equal to 0, so T1 starts conducting from 30 degree. But whenever alpha is equal to 30 degree, T1 starts conducting from 60 to 180 degree. Okay, so the difference will be 120 degree. Okay, then T1 turns off. Okay, and then T2 starts conducting from 180 degree to 300 degree, as you can see from here. Okay, this is the natural waveform from 60 degree, this is 60 degree, and then it will follow the supply input, and then it will turned off, and T2 starts conducting from 180 degree to 300 degree, up to 300. So blue line you can see, this is the conduction time period for T2, and then T3 starts conducting from 300 degree, omega T 300 degree, and it will conduct up to 420 degree. So the green line, the green waveform you can see, that is conduction angle, conduction period for T3. So you can see in the diagram, now we will go to simulation, and as you can see in the diagram, this is alpha degree, alpha equal to 0 degree, and the second diagram we show you three-phase half-wave controlled rectifier with alpha 30 degree. Now we see, and with pure resistive load, now we see what happens. Now conduction angle is changed. Okay, you can go to this gating block and change the conduction angle, and we have changed. Now it becomes 60 to 180, as you can see in the PPT. Okay, you can see in the PPT. Okay, 60 to 180, you can see T1 in this diagram. Alpha is equal to 30 degree. In this diagram you can see omega T 60 to 180. So this is the time period over which T1 conduct. So 60 to 180 first, second conduction period 180 to 300. As you can see, this is the conduction period 60 to 180. Then this is, you can see 180 to 300, and here for third thyristor this is 300 up to 420 degree omega T. Now you can see, you can directly go to run simulation, and now see run simulation, and then select all the three sine waves, then add, and then you get this three-phase supply voltage waveforms. Then select output voltage, V load, across resistive load, then select load current. Then you can see the output voltage is following the input supply voltage. Okay, it is conducting up to here, this point you can measure also up to here. This is the natural commutation is there. T1 turns off here, then T2 is conducting, and then after it is turned off, T3 starts conducting from here. So load voltage and load current both you can see are following the supply input. Okay, now what we can do here, okay, now we go to the simulation, sorry, PPT, what it tells. So this is the alpha 0 degree, this is alpha 30 degree. Now we can add, what we can add, inductive load. Okay, now we are going to add an inductive load, then we will see what happens. Okay, so for that we will add inductive load. So select inductor from here, then connect this inductor into the circuit. Select this inductor like this. Okay, then select, then name it inductor L load, and then give the value of inductance 0.1. Suppose we are keeping Henry, inductance, the value of inductance 0.1 Henry. Okay, now see the output voltage. Okay, now we will see what happens. This was the waveforms for resistive load, purely resistive load. Now we will see what happens when resistive and inductive loads are connected. So select these three supply waveforms, then V load, and then output current, select output current. So this is like this. Okay, output current becomes, as the value of inductance increases, the output current becomes continuous. Okay, now what we will do, we will increase the value of inductance. Okay, as you can see in the PPT, this is the inductive load. When inductive load is connected, this is the waveform of output current, and this is the waveform of output current when resistive load is connected, and this is the waveform of output current when inductive load is connected. So what is happening, the output current becomes continuous. So now we are changing the value of inductance. Suppose this is 10 Henry. Okay, we have selected the value of inductance 10 Henry. Now we will see what happens with the waveform. Okay, again go to the simulation. Now you will see the output current becomes like this. Okay, again you can change. We put 1 Henry. Okay, 1 Henry. Okay, we are putting 1 Henry. So what happens? Run simulation, then select these, and we will see output voltage and output current. So what are the changes that will affect the output current? So this becomes continuous. As you can see, as you can increase the value of inductance, the output current becomes continuous. So this is the waveform of output current when inductive load is connected. So in the PPT you can see this is the waveform of output current. Okay, this is the waveform for resistive load. We can see, we have already seen this. and then you can select any angle, okay, in between 0 to 30 degree. Here these are the waveforms drawn over here from alpha triggering angle between 0 degree to 30 degree. So the conduction period omega t becomes 30 degree plus alpha to 150 degree plus alpha for T1. For T2, conduction period omega t becomes 150 degree plus alpha to 270 degree plus alpha. For third thyristor, it becomes omega t equal to 270 degree plus alpha to up to 390 degree plus alpha, and you can calculate average output voltage by using formulas and RMS output voltage by using formulas, okay, as you must have studied in your theoretical classes. Okay, so these are the waveforms of output voltage. Then this is alpha equal to 60 degree waveforms when triggering angle alpha equal to 60 degree. Okay, so this becomes the alpha equal to 60 degree, so omega t will conduct from 90 to 180. Okay, now we will put alpha equal to 60 in the simulation. Okay, alpha equal to 60 degree. So what happens? See the conduction angle 90 to 180. So change these angle 90 to 180, 90 to 180. Okay, for first thyristor. Then for second thyristor, conduction angle becomes 210 to 300. 210, change this 210 to 300. And for third thyristor, 330 to 420. 330 to 420. Okay, now see, now just decrease the value of inductance 0.1. okay, we will keep this as previous. Okay, now see the waveforms. Okay, now run simulation. Now what happens? Okay, close this and run simulation again. Now what happens at these? Now output voltage becomes like this. This is the output voltage. Okay, because inductance is connected, reverse voltage appears. Okay guys, reverse voltage appears. And what is the load current? You can see this is the load current, and a reverse voltage appears, as you can see here. This is for pure resistive load. Okay, so you can remove first. Okay, this is the waveform for inductive load. As you can see from this PowerPoint presentation slide, we have connected resistive inductive load here. You can see resistive inductive load here, and output voltage becomes like this. There will be reverse voltage due to this inductive effect. Alpha equal to 60 degree we have selected. So this is the waveform of output voltage. And as you increase the value of inductance, your output current becomes continuous. Okay, so what you can do, you can delete this inductive inductance, just delete, and now see what are the waveforms. Okay, just join these. Okay, so now we have only, now this is 60 degree. Okay, alpha equal to, now this is 60 degree. It becomes, you can write here alpha 60. So conduction period starts from 90. So this is the conduction period. Okay, now see, now there is only pure resistive load. Okay, when alpha equal to 60 degree. And now see the simulation. Just cancel this and run simulation again. So what happens? These are the waveforms, and now see output voltage. Because we have selected only purely resistive load, so no reverse voltage appears. You can see no reverse voltage appears, and this is the waveform, and the output voltage is following the input supply voltage. And how will be the, what is the shape of load current? This is the shape of load current, which is also following the input supply voltage. Okay, as you can see here. And when you add inductive load, then the reverse voltage appears in the output waveform. So this is the waveform, as you can see, for purely resistive load. Okay, now add inductance. Okay, now select inductance. Okay, add into this load. Now give name to it, L load. Now select inductance 0.1 Henry. Now see the waveforms. Okay, now again run the simulation. Select 3 sine wave, and then output voltage becomes like this, and the reverse voltage appears. Okay, as you can see here, reverse voltage appears. Now see the shape of load current. This is the shape of load current, and this load current becomes continuous as you increase the value of this inductance. Okay, now we are increasing the inductance 1 Henry. Okay, 1 Henry. So what happens? See again, run simulation. So this becomes continuous like this. Okay, as you can see over here, the shape of current becomes continuous. So that's it for today, guys. This is today's topic was 3-phase half-wave control rectifier, and in our next video tutorial we will discuss about 3-phase fully controlled rectifier. Okay guys, so till then, goodbye. Thank you.